All right, so this is our last study guide we're going to work through. It's dealing with both unit 7, which are kind of our geometry units. So there's a lot that's covered in this study guide. I kind of ran out of space at the end here. We're still able to fit it in 2 pages, so I'm going to try to move quickly through it. Since these units have been most recent, hopefully this is something that you can do without my support, and you're just using the video to check your answers. So for this angle section here, we want to fill out all of the missing angles for each example given. So I've written some principles that we can guide ourselves through this. Example 1, using vertical angles being congruent. So that just means that angles across are the same. And so that means if I have 50 in that left angle there, I should also have 50 in that right angle. The angle across from that. Then in the second principle, angles making a straight line add up to 180. We'll notice that in this case, A through E through C makes a straight line. And so if I take 180 and I subtract that 50 that we already know, that must be what that other angle is, that 130 degrees, which is right here. And then we can use either principle to come up with that final angle of 130. Another principle that we know is that interior angles for triangles add up to 180 degrees. So I should know that 65 plus 57 plus something add up to 180. So I'm going to set up a subtraction problem to do that. If I do 180 minus 65 minus 57, that should tell me what this angle is right here. I'm going to use Desmos real quick instead of relying on mental math. 180 minus 65 minus 57 equals 58. And that's that missing angle. So a similar thing for quadrilaterals or four-sided shapes, but these are going to add up to 360. And if you think about what a square is, it's 90, 90, 90, 90. All quadrilaterals are just variations of that. So I can set up a similar equation here, but this time I have 360 minus 100 minus 80 minus 100. And that's going to equal whatever this missing angle is here. Let me throw that in there. We get 360 minus 100 minus 80 minus 100. So that missing side is 80. And we probably could have just figured that out since this is clearly a parallelogram with opposite angles being equal as well. So last kind of angles principle dealt with this idea of two parallel lines. We have two parallel lines here. The top line is parallel to the bottom line, and we have a third line kind of cutting through them. This is kind of built off similar principles as example 1, but all of our alternate angles are going to be congruent. So our alternate exteriors and our alternate interiors are going to be congruent. So here's what an alternate exterior looks like. 111. Oh, sorry, that's in the wrong spot. We know the alternate interior right now is 111 right there because these are both interior angles. And then I know that because they're vertical angles across, I can place that 111 right there. And then those alternate exteriors are congruent as well. Then the same side interiors, so anything that makes a straight line, those are going to add up to 180. So just like before, we have a straight line there, so I can take 180 minus 111, and that's going to give me an angle of 69. And that can go in all of our missing spots because it's adding up to 180 for a straight line. And then all those same principles of vertical or alternate exterior, alternate interior are in line. Moving on to parallelograms, here's kind of the 3 guiding principles. Opposite sides are congruent, opposite angles are congruent, and consecutive angles add up to 180. So with this, we can just fill in all of the missing info with this parallelogram. Opposite sides are congruent, so I know that this side needs to be 4.5, this side needs to be 3. I know that opposite angles are congruent, so I know this angle is 112. And lastly, to find those 2 angles that we don't know, we should subtract that 112 from 180. which I cannot do that in my head this early in the morning. So I'm going to go 180 minus 112. That gets me 68. And that is what's going in our final missing angles here, 68 and 68. The other aspect of parallelograms we talked about that's helpful is that diagonals bisect each other. Basically, they cut each other in half. So notice how we have this diagram here. We want to find all the missing legs of the diagonal. It looks like this line segment MY is equal to 2. So if it got cut in half by that other diagonal, then that other portion of the segment is also equal to 2. Same thing can be said for this line segment YL. If it got cut in half by the other diagonal, then the other part of it, JY, is just equal to 4 as well. So nothing to do here, but want to really quick talk about a special case. If all these diagonals are equal, like shown here, where we have all 4 of those half diagonals equal to each other, then we have a rectangle, okay? It's squared up. So think about that gardening problem where we measure the diagonals to confirm that it is indeed a rectangle. Moving on to some angles, specifically with circles. The first one is talking about circumscribed angles. Circum means outside or around. So it's dealing with these angles that are kind of on the outside of our circle. And those circumscribed angles, those are always going to be they're always going to add up to 180 with our central angle. So if I know this central angle here of 135 and I'm trying to find x, which is the circumscribed, all I need to do is subtract 135 from 180. And if I do that, let me just double check in Desmos, 180 minus 135, that gives me 45. So I know that x equals 45 degrees there. And similarly, even if we're given the other angle, we're given that circumscribed angle in example 8, we can find that central angle with that same principle. If we just take 180 minus 60, that will give us 120 degrees, which is what x is equal to in this case. Another concept we learned with angles in circles was this idea of inscribed angles. And if they have the same endpoints, they are going to be the same exact angle. So if we're trying to find A, C, B in this first portion, we're looking for an angle that also starts at A and ends at B. And if I look here, I notice that ADB also works. So that means that ACB is going to be 32 degrees, just like ADB is. Okay, similarly, if we're asked to find the measure of angle CAD, so looking down here, going here, and here, I'm looking for an angle that starts at C, ends at D, just similarly. And that looks like if we trace through B as well, that gives me the same angle. So our angle of CAD is going to be 63. All right, the last angles thing we talked about with circles were another inscribed angle thing, this time relating our inscribed to the central. And this is the one that the inscribed are half the size of the central angle. So if I know the inscribed, what I need to do in order to get that central angle is just simply multiply by 2. So I'm just going to kind of make a quick note there, multiply by 2. And if I do that with 62, that gives me 124 for that central angle. Now, if I'm going the other direction and I want to move from the central angle to the inscribed angle, now I need to divide by 2 because I'm going in half of that central angle. So 98 divided by 2 would give me 49 there as our inscribed angle MLN. All right. Another thing we learned about with circles was this idea of arc lengths and sectors. And if we look down at these diagrams here, you'll notice that there is some sort of arc here that's tracing not the whole circle around, but almost all the way the circle around. And so this arc length is going to be the length of that area, or that line there, that partial circumference. A sector, on the other hand, it's going to kind of be the associated shaded area traced by that arc there. So in all of these cases, we are going to have formulas that are fractions times whole. Fractions times wholes. So in our degrees, our fraction is always going to be whatever angle divided by 360. With our radians, it'll be divided by 2 pi, because in both those cases, that makes a full rotation. And with arc length, it's going to be times our circumference formula, 2 times pi times r. With our sectors, same fraction setup, degrees, 360 on bottom, radians, 2 pi on bottom. But then we're just using our circle area formula, pi r squared, in both of those cases. So to find the arc length in example 13, where we have, and actually we want to find the arc length and the sector area for example 13, we have an angle of 315, and that is in degrees. So I'm going to use my formula L equals 315 over 360, and then I'm going to multiply by 2 pi times r, which in this case is 11, and that will give me a arc length of, let me clear out some stuff in Desmos, 315 over 360 times 2 pi times 11. That gives me 60.5. And let's just round to one decimal place here for the sake of space, and that is in feet. If I'm finding the sector area, however, I can use that same fraction setup, 315 over 360. But this time I'm going to multiply by pi r squared, so pi times 11 squared, and that should give me the sector area, which if I type that into Desmos, 315 over 360 times pi times 11 squared, we get 332.6, and that will be in feet squared. Okay, we can repeat that for example 14, except this one, notice how our angle measure is in radians. It's 3 pi over 2. So for arc length, I recommend using this simplified version of the formula. Notice how in the full version, the 2 pi here would get canceled out with this 2 pi. So all we're left over with is that theta times r, that angle times r. So in this case, my length, arc length here is just going to be 3 pi over 2 times r, which is 16. And if I throw that in, 3 pi over 2 times 16, I'm going to get 75.4. And this is in feet. And then that sector area, a little more complicated equation. Make sure we're careful while typing this into Desmos. This fraction now, 3 pi over 2, is going to be divided by 2 pi times pi r squared, which is 16 squared. So I'll throw this into Desmos because I definitely can't do this on my own. Notice how I'm going to set up the fraction first. I'm going to go put 2 pi on the bottom. Then I'm going to go up top and set up that other fraction. So I got 3 pi over 2 up top. And it's key to make sure that we are putting those in the right location. That big fraction should separate the top fraction and 2 pi. And then I'm just going to multiply by pi r squared, so times pi times 16 squared. That gives me 603.2 as my sector area. And that is in feet squared. Last thing we learned about with circles was this intersecting chord theorem. Basically, if we have two lines across our circle going edge to edge, we can multiply those individual segments, A times B, and that should get us C times D. So if we're solving for X in this one over here, we have this line segment here, 9 and 16. Let's call that A times B. So 9 times 16. We can say that is equal to this other line segment, which has legs of 8 and X, so 8 times X. So all we really need to do is take this 9 times 16, which gives us 144. That is going to be equal to 8x, and then we can simply divide by 8 on both sides and come up with our x value, which, let me just do that in Desmos because my mental math is not there right now. 144 divided by 8, that gives us 18 as our answer for x. All right, this was kind of a random topic we had, but in example 16, we're talking about our different triangle centers. Even though we covered four, there's three that are important. Two of them create circles. If we create a center by using the perpendicular bisectors of each of the sides of the triangle, this center point is then called the circumcenter, because we can then take that center point and draw a circle around our triangle that hits all three edges. So that is built up from our perpendicular bisectors. If we make a triangle with our angle bisectors here that split the angles in half, those are going to make a center point that creates a circle inside our triangle. And that's going to mean that all three of the things that touch are equal. Those are basically our radiuses. This is going to be the incenter. And the last one we learned was definitely the weirdest one. This is called the centroid. It has some properties that you're probably going to work with in Math 4 down the road. But this is made by connecting our altitudes. So the midlines of one point's connecting up to the point of these other points, that will give us our centroid point there. All right, lastly, I want you to take a pause of your screen and then fill out as many formulas as you can by memory, because these will just help us working with our various geometry problems. Once you've given that a go, unpause your screen. I'm going to kind of write them out, and you can check your work. So I filled out all of these. A couple things to kind of maybe notate on your notes. Anytime you guys see this L here, that is length, okay? Make sure you know that that is not a 1. Another thing to notate, if you look at all of our area formulas, all of them take 2 dimensions and they multiply together. W squared, L times W, base times height, R squared. Whereas our volumes, those are 3 dimensions. They're going to take 3 dimensions and multiply together. Length times width times height, R squared times H. Length times width times height, R squared times H, R cubed. To remember the different fraction setups, think about how, hey, in 2 dimensions, we are dividing by 2 with our area of a triangle, or multiplying by 1/2. With our 3 dimensions for our pyramid and our cone, we are dividing by 3 or multiplying by 1/3. And with all of our volumes, we're taking some base area, like a length times width, and we're multiplying it by the height. Or we're taking some base area, like this pi r squared, and we're multiplying it by a height.